Well, good morning, everyone. Thanks for joining. So today we have ESIC and AGI seminar, which will be on GridSandbox, and the title is End-to-End Analytics for Grid Architectural Design and All Hazard Assessment. And we have pleasure of having two speakers today because it's a AGI seminar. So we have from PNNL, Dr. Dexin Wang, and also from WSU, which is Dr. Sadanandan. And, they will talk about this soon. So Dr. Dexin Wang is an electrical engineer in the optimization control group at PNNL. And he got his PhD from Colorado State University, Fort Collins in 2019. And he worked on several projects related to grid resilience and transactive systems. And Dr. Sajan is a postdoc researcher in Energy System Innovation Center at WSU. And he has been working mainly on different T&D analysis for cyber physical resilient design. And he received his PhD from IIT Roorkee in 2016, and then worked in GE in Hyderabad for synchrophasor wide area monitoring applications using GE Terra for 3 years before joining here. So with that, please welcome Dr. Dexin Wang, who will talk first, and then Dr. Sajan, and then Dr. Dexin Wang will take over. Thanks, and it's all yours, Dexin.
Thank you for the kind introduction. Let me first share my screen. Okay, so welcome to today's webinar. And so today our presentation will be about the GridSandbox. It's focused on an end-to-end analytics for grid architectural design and all hazard assessment. This project is part of the effort of the WSU PNNL Advanced Grid Institute. And this project is designed to further nurture the joint capabilities in areas of strategic importance to the electrical power grid research in both institutions. Yeah, so first, I would like to thank the excellent joint team of researchers from both WSU and PNNL. This project wouldn't have succeeded without their hard work. So first, I will give a brief overview of the project as a whole, and then Dr. Sajan will talk about the communication system modeling part, which include the component level modeling and network level modeling. And then we will walk through the co-simulation integration used in this project, and followed by a simulation case study and a demo. So as the grid evolves, it's getting more and more complex every day. And this significantly increased complexity will affect the efficiency, reliability, and resilience of the grid. And so that's why we need a new grid architectural design to prepare the grid to face such challenges. And it involves new elements and new interactions among those elements. And also, since we have a new, we need a new grid architectural design, we need the ability to assess these various grid architectures and the associated hazard. So that's because with the new grid architecture, it could potentially expose new hazards to the grid operations, and we need a tool to assess those analyze those hazards. And so Dr. Jeff Taft and his team has come up with, have done excellent work in this area, involving the grid architecture in the GMLC grid architecture project. And it includes both architecture in the power system domain and also the communication domain for the power grid. So this project also leverages previous work on GMLC Helix, which developed a open source co-simulation platform that facilitates the co-simulation across multiple domains. So this is a non-exhaustive list of the supported simulators in transmission, distribution, and communication systems. So in this project, in the first phase of this project, will involve the GridPack simulator in the for the transmission domain, and Ns3 simulator for the communication domain. So the goal of GridSandbox is to build an open access modeling and simulation environment, and the challenges to solve the challenges for grid architectural and all hazard assessment. That include first is the lack of effective approach to leveraging existing efforts and technologies, and also the lack of necessary access, expertise, and hardware software resources. So we have, in the previous projects, we have built Helix, and we have built individual softwares, simulators for each domain. And but to use Helix and use these highly specified simulators will require significant expertise and know-how, and that may not be available to especially in the smaller institutes. And so that's why we want to provide this easy to use, user-friendly open access environment where people can come in and play with the data, the model, and the software and hardware capabilities we have. And from a software perspective, the architecture is like this. So the goal is to be modular and to be portable, scalable, and user-friendly. So here, the user can input the model coefficients for a particular model in the, for example, in the power system. For example, the coefficients for the power system stabilizer, and then but also the system configurations for a configuration for a simulation platform. In this case, maybe a GridPack configuration, and also provide the scenario design for the co-simulation. So the users can choose which simulators to use, for example, Ns3 and GridPack, and how to connect them together. These are all done through a web UI interface. And the web UI will take the user input and send that to the backend. So this core simulation engine can do the work and get the required data from the database, and then return the result back to the user interface. Yeah, the first so for the phase one of this work, we want to focus on the comparison of last-minute communication architecture and it's basically a PMU communication network for the wide area power grid. And it mainly involves the old layered hierarchical PDC network design and versus the new layered design. So we will talk more about that in the use case part. And here I want to show the software integration. So here the Helix is a hub to coordinate different simulator for the co-simulation. And the GAUSS bus will take care of data model interoperability, and also to coordinate Helix and all the start and stop each simulators. And then it also communicates with the web portal, and which handles the user input and visualization of the results. So next, we'll hand over to Dr. Sajan for the communication system modeling part.
Thanks, Dexin. Hi, everyone. Like we are working on this project to support like PNNL in the development of the communication framework. So in this, can you go to next slide, Dexin? Dexin, can you take next slide? Thank you. So as you know that the modern power system has progressively developed into multi-dimensional heterogeneous cyber physical system with complex interdependency between power system and the communication system. So while modeling a power system, it is essential to consider communication system and model it for the planning, operation, and analysis of power system. And another aspect of is the grid architecture, because different architecture will result in different interaction between entities and entity class. So for any communication architecture, it is very important to like identify like which communication architecture we are using for modeling the network. For example, like it's a like whether it's a siloed architecture the power industry used to do communication, where each application uses the dedicated network for monitoring and control, or the recommended layer architecture where different applications share the same physical network infrastructure. So the main objective of this work is to evaluate different communication architectures and identify what are the advantage and what are the disadvantage of each communication architecture. And with the development of like new technologies, which is like one of this is like 5G, which is a new technology in the communication industry. So that like which uses like radio access network, or the core, which is like network slicing, or the software defined networking, which is like how it's a quite mature in the communication, and we can introduce this to the power system and come up with new applications to help and manage the communication network to improve the monitoring and control of the grid. And there are also different control algorithms which are developed by different researchers, which are like communication aware and communication efficient control algorithms that take into account the communication latency when they build this. So we need a tool which can evaluate these different combinations of like how we can the different combinations we have for the communication architecture. We have different algorithms how we can evaluate before it's applying to a real world system. So GridSandbox is a project which gives a platform to do this evaluation. Dexin, can you go to next slide? Thank you. So for this, we are using building our communication architecture using Ns3 Simulator. So Ns3 Simulator is a discrete event network simulator for internet system targeted primarily for research and educational users. It is an open simulation environment and provides models of how data packet networks work and perform. Network is built to perform the studies that are more difficult and more not possible to perform with real system, and study system behavior in highly controlled and reproducible environment. And it's also learn how network works. There are different use cases, and it like NRC has been used in the past for in almost all the system which is using a communication network. So some of the examples which are listed here is uh, like vehicular ad hoc network or long range wide area network and cyber physical system testbed building modeling for the smart grid. So these are the few examples which uses network. So here is a high level overview of the capabilities of NS3. We have used like a TCP IP model or OSI model which has different layers, and each layer has its own process, and we can use NS3 to simulate each layers differently with different, like we can simulate here internet or non-internet based system, wired or wireless simulation, which involves like for the layer 1 and 2 we need like we can use Ethernet, Wi-Fi, WiMAX or 5G itself, and they are different. And for having a network we can have either a static or dynamic routing protocols. And when it comes to like transportation layer, we can use either UDP or TCP protocol. And in the application layer, we can have different protocols like a web-based, or it can be a DHCP or a synchrophaser protocol, which is C37.118, which I will be discussing in the following slides. Next slide, yeah. So in this our effort, like we have divided the communication modeling in NS3 into two different categories. The first is the component level category and the second is network level. So in component level, we have defined like what are the different components we need to construct this complete network architecture. So that components which we build here in this project is like PMUs, like phasor measurement unit, as PDCs, that is like a phasor data concentrator, and synchrophasor thing as like that said we need like a interface between a grid pack and the NS3 model. So how we are doing the interface, and then a historian app which will like finally dump all the logs, all the data into a log file or a database which can be further used for the application. So I will be going with each component in detail in the following slides. Then comes the network level. In the network level, we are like we are developing network models, then building like representative low latency paths, then assigning different characteristics, like we are assigning like what should be each device do, then integrating like different applications on the node like PMU, PDC, they have different applications, and then we are doing all this analysis with different network configurations. Next slide, please. So in that level, we like first start with the PMU modeling. So this is an app which has, so as a real PMU has different steps. Like the first step, which will be like taking an analog signal, sampling that, and then filtering, because in real data always have some noise, so filtering it. Then we have to do a phasor estimation. Once the phasor is estimated, that has to be used like a time synchronization and for time tagging. Once that is done, then the phasor data is collected and then reported. And finally, the PMU should create a data packet which is in the which is implemented with the standard, that is 37.118 synchrophasor standard, which has a sequence of like data which we say that we have a header, then we have what is the second of when we captured it and what are the data, and then we will give a check bits for that. So in that form we will pack that data and then it's sent to the PDC. So in this, the PMU app which we build with the PNL, that has like, that is getting us direct phasor estimation. So the first three components which is shown here in the figure, that uh, we are not haven't considered in this app, but we have the capabilities to add the filters, and we can add noises to the simulated measurement and then add filters and remove that. So that capability we have. But now, right now, we are receiving the PMU data, and then we are packing it and sending that data to PDC. Next slide, please. Next slide, Declan.
Yes, there is some delay.
So in this, yeah, there is some delay. Sorry for that. So the PDC modeling. So in this, we are trying to capture all the features, most of the features which are there with the PDC, that is phasor data concentrated, which is basically what we have. It has to do, like, it has to collect the multi streams of PMU raw measurements as the input and output a single stream of concentrated PMU raw measurements, and then complain to IEEE C37, that is a synchrophasor standard, and then send it to the historian, or support, like send to the application layer using a TCP or UDP. So as a basic implementation, we have like created a basic features, like we have created a time buffer. So it will receive all the PMU data which is configured to a particular PDC, and like wait for that time buffer, or once so if the arriving packet is from the previous timestamp buffer which has not been sent to the super PDC, then it will discard it. Otherwise, the packet will be added to the buffer. And once the data is there, then it is concentrated into increasing order of timestamp and sent to the super PDC as one packet. Then the PDC is installed to receive the data. All this we have implemented like with the standard of synchrophasor standards. Next slide. So this is like another component which we have developed is synchrophasor sync app. So the main aim of synchrophasor sync app is to publish the readings from the PMU measurement into Helix along with these attributes. So we need a co-simulation environment where
the slide was not coming very well. Now it's good. Yeah, go ahead.
So my voice is
no,
audible?
the slide was not visible very well. It was not very. It has some fuzzy character, but now
yeah, Dexin. I think Dexin is sharing that.
Yeah, now it's okay.
Okay, so okay, so so in synchrophasor sync app, we are like trying to create a simulation, like co-simulation environment between, so it has to link with the higher, like Helix, and then Helix to Ns3. So this communication model, so for that we required a synchrophasor sync app which will do, and there are different instances or the parameters which we have to define for the synchrophasor sync app, that is Helix publication pointers. It is like it retrieve using the publication key, then Helix publication key. It is a string value which contains the publication key. Then expected stream ID, store all the expected stream IDs. IDs means the PMU IDs. And then it's a like store all the expected PMU IDs that the node is receiving packet from. So all these informations are the inputs for this synchrophasor app. Let's see next slide. So the next component which we build in this project is the historian app. The main aim of this historian app is to record the data which is coming and either store them or print them into a log file for further application, or even we can store this into, in a future we can store it to a database so that different applications can use it for the further analysis. the historian app opens and listens on a port in order to receive the packet sent from the PMU. So it also have different following parameters that like it is using, that is HELIX publication pointers. The publication is an object which it is retrieved using the publication key, and it is also associated with a key. It is a string value which contains the publication key. So all these components like PMU, PDC, synchrophaser, sync app, and the historian app combines, and they will be are used for a network modeling. Lexing, can you? Yeah, thank you. So this is in the network level modeling. So this is example of a network topology. So where different substation is sending or communicating sending the data to a control center, and each substation has different components. They can be PMUs, and each PMUs like in this network topology, they are like connected in a mesh way. So there can be a different configuration. They can be connected to a point to point, or a centralized communication can give them. And once all this data is sent to the aggregator ring in this model, that is a PDC, where the phasor data concentrator is there, and it will collect all the data. And from different substations, all this data is sent to a control center using a core backbone, that is the architecture. So this is one of the example, and there can be different combinations and different type of architecture which can be used depending upon different utilities. Next slide, please. Is this uh, next slide, Texin?
Yeah.
Yeah, I do see a next slide.
Sorry, so it was delayed from my side. So so in the network level modeling, we have defined, like we have to define what is the nodes, each nodes in the NS3, and what are the channels or links which is connecting these different nodes. For in nodes, there are different attributes which we have to set, like ID, which will give the name and the number for, or the name and the number for that particular node, and the locations which gives the coordinate where exactly the node is associated. And we also have to define the application, like which type of node is that, whether it's a PMU node or it's a PDC node or it's a super PDC. We have to define that. And then we have to also define some attributes, like each like what is the sampling rate, what is the protocol which is going to follow, and what is the control parameters. So all these attributes we have to define for each node. And then when it comes to a channel, we have to define like this channel, we start the two IDs which is connected to, which this channel is connected to, and then which type of like connection it is, like whether it's a fiber or microwave or it's a power line communication. And then what is the length of each channel, what is the capacity or data rate, and the how much delay it can happen. So all these things we have to define in the NS3 modeling. So there is two like there is a network which we have defined here, like where there are 6 PMUs, where first 2 PMUs is connected sending data to PDC1, and the 3 PMUs are sending data to PDC2, and the last, like the 6 PMUs sending directly data to the super PDC. So, and these two PDC1 and PDC2 are sending data to. So what we have defined different, like how this each node. So the first 6 nodes are like a PMU, and then we have defined the other 3 nodes as a PDC. And we have defined like the data rate and the delay for each channel from the first 2 PMUs. So to the PDC is set to 50 Mbps and 2 millisecond delay, and the data rate for the all other PMUs we set to 30 megabytes per second, and delay as 3 milliseconds. Sorry. Next slide, please. So here is a small demo where we are sending the data from different nodes to the PDC. So here you can say like how the data from each PMU is sending to first PDC1 and PDC2 and from PDC to super PDC. So from here, I will hand over to Dr. Destin again, and now he will discuss about the automation simulation setup part in this project.
Yeah, thanks, Sajan. Yeah, so we have seen that Sajan have showed us that we have built the capability of both component level and network level modeling. But as we have seen, we need to configure those components and network node connections, channels for each of those components. And that may be okay for a small scale simulation, but as the scale of the system grows, and that quickly becomes very tedious, if not impossible. And so that's why we have developed this automated simulation setup capability. And we think it's necessary for large scale studies. And it's a YAML-based configuration file. All the node and channel attributes and their values, how are they connected, are all specified in these in this configuration file, and including what apps, what applications are installed on each node, and what are the attributes for each of these applications. And we have utilized the Ns3 attribute configuration mechanism and integrated that together with this, so that the type ID and the attribute name and values can be directly inputted in the configuration file. And we have built a topology helper that can read this configuration file and set up the network, set up the entire simulation automatically. And here is just an example of using that automated configuration for a Illinois 200 bus system, where we've built a synthetic communication network leveraging an algorithm developed in another project, and it is visualized in NetAnnon, which is the visualization tool in Ns3. So next, I will talk about the co-simulation integration based on Helix. So GridSandbox uses Helix for the co-simulation capabilities. And Helix is a flexible and scalable open source co-simulation framework. It is developed previously as a GMLC project, and it's still under active development today. So, and it can handle diverse simulation types, including continuous and discrete, steady state or dynamic, and also time series simulations. And it also supports multiple platforms, whether it's a HPC, it's cloud deployment, or it's a single workstation, or even on a laptop. And it supports multiple standards that are very handful when building co-simulations. So besides Helix, we use GAUSS as a middleware platform. We leverage this GAUSS platform to manage data and services. So it is designed as a prototype for future data analytics and integration platform, and it supports different power or different data model formats, and it can support data source abstraction, and also some simulation workflow management, which is very very important for a multi-user or multi-simulation instance environment. So here is the architecture of the GridSandbox. So here from the GOS platform viewpoint. So here we have the user interface, and we have the message bus from GOS, and it takes the user input and feedback the simulation results from using this message bus, and it manages the Helix broker and each of the individual simulators, and it also queries a database to get the necessary model data that's needed to do the simulation, co-simulation. Yeah, and in this specific project, we to build a Helix-based co-simulation, we need to build the cyber physical. Build this for a cyber physical system. We need to build it for both sides of the system. So on the on the physical system side, it is simulated with GridPack. On the cyber side, it's simulated with Ns3, and it includes power system dynamics, and includes PMU measurement, PMUs, and also controllers, and as well as the telecommunication wide area network in between. So the co-simulation challenge, the two of the most important co-simulation challenges is first the clock synchronization, and also the data exchange. We'll talk about that in a moment. So here I'd like to briefly introduce the key concepts in Helix. So this figure on the right shows the most common Helix architecture for a Helix-based co-simulation. So we have one broker sitting in the middle, and we have a Helix core for each simulator or for each federate. And federate is a name for a running simulator inside a Helix-based co-simulation. And there are three types of federates. One is a value, message, and and combination. So their main difference is the type of data exchange with the rest of the federation. So with other federates. So for value federate, it exchange persistent value information. And for message federate, it exchanges packet type messages. So, and combination federate can have both type of messages. And for the core of each federate, there are also different types of cores. So the simplest one is test, and there are interprocesses, which essentially runs each federate on the same computer, and it uses interprocess communication for the communication between cores. And the most common core type for Helix is 0MQ, which uses this 0MQ library to handle the communications among the core and broker and between them. And for message types, I've talked about that for different federate types. There are two types of messages. One is a value message, the other is a packet-based message. Value message is mainly used for to mimic a physical connection between two simulators. For example, if we simulate the transmission and distribution level, we will have a value message between them to exchange the voltage and power flow across at the substation. And the broker sits in the middle to manage the data exchange and the clock synchronization among all the federates. Yeah, this link for more detailed explanations of these concepts, you can go to this link. So here with this slide, I'd like to show a simple example of the synchronization of and data exchange in this project. So here we have GridPack as a power system simulator, has a fixed step size. And in this example, I show it as a 1 millisecond step size. And Ns3 is a discrete event simulator. It does not have a fixed step size. So here, as you can see, it can be granted, it can come with different size of steps. So at the beginning of this co-simulation, each federate or each simulator will request a time that it like to go to. So here for Ns3, since it has the Pmu inside it, it needs the first request it has is to go to the 20 millisecond time step, and so that corresponds to the sampling frequency of the Pmu of 50 hertz, 50 times per second. And for the GridPack, it requests to go to the first millisecond, and the Helix broker will will look at their request and grant the request that that's earlier in the timeline. So in this case, the Helix broker will grant the 1 millisecond time to GridPack, and GridPack will do its simulation for the 1 millisecond step, and then it will request it to go to the 2 millisecond time step. And this goes on until at one point it requests a 20 millisecond time step. And here at this time, the Helix broker will see that both Ns3 and GridPack request this time step. So it will grant this to both of these simulators. And so at that time, the GridPack and Ns3 can do their work respectively for this time step. And this work this continues until the end of the co-simulation. And so next I'd like to introduce the use case we focus on in the phase 1 of this project. So here we want to compare the original NASPnet and the NASPnet 2.0 communication network architecture. So for the original NASPnet, we have a data bus over the top, and we have over the top PDCs and gateway network paradigm. We can see here we have PDC stacking, and so we have maybe have a PDC at the utility level and have a PDC at a regional ISO, and so there are multiple levels of PDC that one PMU measurement need to traverse to get to its destination, and that can potentially cause high latencies on top of the normal network latency. And so that's why Dr. Jack Taft have proposed this NASPnet 2.0 architecture, where instead of a gateway network paradigm, we adopt the core edge paradigm, which is prevalent in modern communication networks. So to eliminate the PDC stacking and build PDC as a function, not a standalone equipment or device sitting at the core of the network, which slows down the data transmission. And also this the CS 37118 protocol is over UDP protocol and or the STTP instead of TCP. And the goal is to achieve low latency. And here we'd like to investigate how the network communication network issues, most importantly delay and packet drop, will impact the wide area control, and in this case the wide area power system stabilizer performance. Yeah. And we have GridPack at the to deal with the PMU measurements and also the wide area control, and we have N3 to deal with the network and the so the PMU message encapsulation and the network. So the GridPack is a framework to develop at PNNL. It consists of a set of modules that facilitates the design of parallel to using the high performance computing platform to do power grid simulations. And it includes many different modules that can facilitate such simulation design. And we've built this 39-bus grid model inside GridPack for this project. And also on the communication side, we've built this 39-bus system, the communication network for this 39-bus system, where we treat buses connected directly with a transformer as one substation, and which corresponds to one communication node in the network. So here is an example of the data flow where the PMU measurements are generated at the GridPack side, and then transmitted to the sent through the Helix broker to the Ns3 side, and then at Ns3 side we encapsulate this raw measurement with different protocols for. Including the the synchrophasor protocol, and also the UDP for layer 4, the transport layer, and IP, etc. And do this for each of these measurements. And then these packets are sent through the communication network to the destination. And there, the packet is decapsulated and transmitted and processed. Here we only need the difference between these frequencies and then transmit back to the GridPack side. So for the UI and user experience, we put each component inside a separate Docker container to facilitate the deployment on cloud, and also to facilitate easier scalability in the future. More and more users are using this platform. And here we have a short demo. And since I'm not sure whether we have enough.
We host our web server internally on Linux machine.
I'm not sure, so could you, if we have enough time to handle the questions, so please put your questions in the chat window and we can we'll follow up with the email.
And theoretically, anyone who within the PNNL network should be able to access this web tool. So the first thing to using the tool is really log into the system. Currently, we can using tester as the temporal testing account. If you click login, you will see there's like a dashboard. So in the dashboard, the left side really showing the available tool. Currently, we only have one. And then if you click this icon, you will see it's basically a pop-up a window which asks you to type in name. With the name, we can create a new like a project for this kind of tool. In the current demonstration, we already have an example set up for demonstration purpose. So we just need to click edit, and then we can basically enter in the detail for this project. As you can see, the project actually having two sections. One is called the input. So in the input section, we basically collecting the user input through the simple like a text box or the drop box. And you can see right now the output section is kind of disabled because right now there's no like a result to show. In order to like run your simulation, the first thing you have to determine how many cases you want to study. So by click the case number drop box, you can basically selecting the number of cases you want to start. So notice that if you based on the input from this drop box, you're actually having different like number of input you have to specify. That can automatically change based on the input. And in our case, for demonstration purpose, we want to study the same system with different like communication delay. So for the case 1, we sent in the delay to be 2 milliseconds. For the case 2, we sent in the delay to be 100 milliseconds. And for the last case, we want to study the scenario when the delay equal to 150 milliseconds. Once we finish all the input specified, we just need to click the run. And you can see immediately there is like a label showing saying that simulation is running in backward. And at the same time, if you check in the like the log from the GOSPAS side, you see there is some like logging showing that the simulation is actually instantiated and also like entering the dedicated directory to running individual simulator. And then user just need to wait until the back end to finish all the simulation. It usually takes several minutes to finish. From the log, you can see actually there is several messages saying that, for example, this one basically showing we have a new like simulator log assigned for like Ns3. Once the simulation is finished, you see there is a message saying that we kind of stopping the existing process and then starting a new process. And in the meanwhile, you see we kind of having the auto refresh function, which refresh the web page frequently. So once there's an update, we can basically automatically seeing those updates reflect in this web page. And now we kind of finish we kind of processing the simulation for the second case. And you can see that when the simulation is run, all the input are basically temporarily disabled. So you are not allowed to changing the input while the simulation is running. But once the simulation finish, then you are able to modify the input again. I think now we are kind of entering the submission for the third case, which is the final case. Yeah, this is like a very initial like a demo version of the web page, And in the future case, we also consider to basically, instead of showing those back-end information with a terminal box, we want to also allowing the web page to display those log information so that the user can understand what's happened in the back-end side. So once the simulation finish, you will see the output will become enabled. So in that case, we can basically click the output to see the results. Just give a few more minutes to let the simulation finish. And you may notice that we also added some annotation so that once user using the mouse to click the label of the different input, you can actually see all this detailed explanation for individual input.
So, Dexin, I think we should allow one or two questions.
Yeah, this should finish very soon.
我觉得这可能是后台那个出现问题了，可能
卡住了。
Yeah, I think so this is the simulation result we get from the backend, and so this shows the generator rotor speed at with different communication delays, and so as we can see, with the larger delay, it causes severe oscillation at this generator. And with that, I think we can go to the question.
Thanks. So I think there's so far there's only one question, which is about potential application for the graph for the network topology. And I think one was NASPNet 1.0 and NASPNet 2.0 compression. What other application you see? Dakshin or Sujan, who would like to take that question?
So, it's Sajan here. So, the different applications, like it depends, like we can use. So the main purpose here to like we can model it for different architecture, like okay, so how for same network we can analyze for different different architecture, and how the latency and the other performance which are there, we can analyze that. And it can be used for different application like RAS, where it's a control application which is very tightly dependent on the time delay and the data flow between the network and the RAS application. Then there is another is oscillation monitoring applications, where we are monitoring the, like as Dexin shown the demo, where we are monitoring the frequency difference. So all these things we can use this, and we can suggest in the planning phase, like where we should keep the PDC or PMU, what should be the network protocol, what should be the like type, and the capacity.
Okay. So the second question I already answered by Dexin, the generator.
Yeah, so I'm not sure if this answers your question. The curve shows the generator speed in 3 cases.
Yeah, so I think we are right on time. So maybe we can discuss some of the question offline. And thanks again, everyone, for joining. And if you, I don't know if you have a slide with the emails, Lexin. Yeah, probably not. But anyone else?
Fast at PNNL.
Yeah, thanks. So anyone who have question, please send us email, and I'll forward to them. Thanks, everyone, and have a great day, and look forward to the next webinar on next Tuesday. Thank you.
Thank you, everyone.